Let's see how we can use arguments based on dimension to tell whether a linear function f is invertible. So we know a function is invertible if it's one-to-one and onto. A linear function is one-to-one if its kernel is trivial. That is, if its kernel has dimension 0. And now, what about onto? Well, a function is onto if its image equals its codomain. Recall that the image of a function f is the set of all vectors f of v where v is in the domain. Long back, we learned that the image of a linear function is a vector space, a subspace of the codomain. Now, how can we tell if the image of f equals the codomain? We'll use something I call the dimension lemma. Suppose big U is a subspace of big W. Then the dimension of big U is no more than the dimension of W. And if the dimension of U equals the dimension of W, it must be that U equals W. Well, let's see a proof. We start with a basis for big U, U1 through UK. By the superset basis lemma, we can take that basis and extend it to get a basis for W by adding a few more vectors. So there's a basis B for W that includes U1 through UK, the basis vectors for big U. Well, that shows that K, the number of vectors in the basis for U, is no more than the cardinality of B. And in fact, if K equals the cardinality of B, then we must not have added any vectors to get B. So the basis U1 through UK of U is also a basis of W. And therefore, U has to equal W. So that proves the dimension lemma. Now let's see how we can use it. We'll apply this second property, property D2, with big U being the image of f. Remember, we want a criterion for when the image of f equals the codomain W. Property D2 shows that U equals W if the dimension of U equals the dimension of W. That is, if the dimension of the image of f equals the dimension of W. So we can conclude that f is invertible if and only if the kernel has dimension 0 and the dimension of the image equals the dimension of the codomain. Now, how does that relate to the dimension of the domain? One might conjecture that for a function to be invertible, the dimension of its domain should match the dimension of its codomain. This corresponds to the intuition that the vectors in the domain can be made to correspond with the vectors in the codomain. We'll eventually prove this conjecture, but we're going to take a little detour. We're going to start with a linear function and extract from it an invertible function. So here's a picture of a function whose domain is V and whose codomain is W. What we're going to do is extract an invertible function from this. How does this function fail to be invertible? Well, one thing we note is that it's not onto. There are elements of the codomain that are not the image of any elements of the domain. So let's get rid of those elements. We'll set the codomain of the function that we're extracting to be just the elements of the codomain of the original function that are images of things in the domain. Now, we can make it one-to-one by choosing for each element in this new codomain just one element that maps to it, and we throw away all the other ones. That's the intuition for extracting an invertible function. So let's go into this in more detail. The first step, starting with a linear function f, whose domain is V and whose codomain is W. The first step is to choose the smaller codomain, which we'll call W star. The second step is choosing a smaller domain, which we'll call V star. And then we'll define the function f star with domain V star and codomain W star. We use the same rule to define F star. So F star differs only in that its domain is smaller and its codomain is smaller. We end up choosing a basis for V star and for W star. All right, how do we choose W star? As I said before, we're just going to let W star be the image of the function f. That is the set of all elements in the codomain of the original function that are the image of elements in the domain. And let's let W1 through WR be a basis for W star, our new codomain. Now we'll choose the domain. Let V1 through VR be pre-images of W1 through WR. That means we choose V1 through VR to be vectors such that f of V1 equals W1 and so on up to f of VR equals WR. And we define the new domain, V star, to be the span of vectors V1 through VR. We're going to show that the resulting function f star, whose domain is V star and whose codomain is W star, will show that it's onto and that it's one-to-one, namely that its kernel is trivial. And we'll also show that V1 through VR, the pre-images, form a basis for the new domain V star. First, let's look at onto. Let W be any vector in our new domain W star. Well, because W1 through WR form a basis for W star, there exist scalars, alpha 1 through alpha r, such that our vector little w can be written as a linear combination with those scalars as coefficients. Now, because f is linear, when we apply f to the corresponding linear combination of V1 through VR, we get that linear combination of W1 through WR. So that shows that this vector W we started with is the image of something in the new codomain, namely the linear combination of V1 through VR given here. Now let's show one-to-one. By the one-to-one lemma, all we need to do is show that the kernel is trivial. That is, that it consists only of the zero vector. Well, suppose little v star is in big V star, and the image of little v star is the zero vector. Because V star is the span of elements V1 through VR, there must be coefficients, alpha 1 through alpha r, such that we can express little v star in terms of V1 through VR. Applying f to both sides of this equation, on the left side, f of v star equals the zero vector. So we get this. Let's apply f to the other side. By applying linearity, as we saw before, we get this linear combination. Now, W1 through WR form a basis for W star, and therefore they are linearly independent. We've gotten 0 as a linear combination of those vectors. Therefore, the coefficients must all be 0. And that shows that, in fact, the vector little v star, which is the corresponding linear combination of V1 through VR, is the zero vector. All these coefficients are 0. That completes the proof that the function f star is onto and one-to-one, and therefore it's invertible. And here's the promised bonus. We want to show that V1 through VR form a basis for the new domain, big V star. Well, we defined big V star to be the span of V1 through VR. So in order to show that V1 through VR form a basis, all we have to show is that they're linearly independent. Well, suppose you can get the zero vector as some linear combination of V1 through VR. On the left-hand side, applying a linear function to the zero vector always gives you a zero vector. On the right-hand side, as we saw before, applying f to this linear combination of v1 through vr gives you the corresponding linear combination of w1 through wr. Now, w1 through wr are linearly independent, so it must be that these coefficients are 0. And that shows that the only way to get 0 as a linear combination of v1 through vr is with the trivial linear combination, where all the coefficients are 0. We've shown how to extract an invertible linear function from the linear function f. Let's see an example of this construction. Let A be this matrix, and let's define the function f from R3 to R3 by the rule f of x equals a times x. Now, we define the new codomain w star to be the image of the function f. That is, the column space of the matrix A, which is the span of its columns. Now, one basis for w star consists of w1 and w2. Next, we find preimages of these vectors, say v1 and v2. These are preimages because a times v1 equals w1 and a times v2 equals w2. Next, we define the new codomain to be the span of those two vectors. Then the function f star from big V star to the image of f, w star, is onto n1 to 1, and therefore invertible. Now, we're going to show that the original function has the following property. That the original domain, big V, is the direct sum of the kernel of f with this smaller domain, big V star. So we have to prove two things. For the direct sum to even be defined, we have to show that the kernel of f and big V star share only the 0 vector. And once we've done that, the direct sum is defined. To show that these two things are equal, we have to show that every vector in the original domain, big V, can be written as a sum of a vector in the kernel of f and a vector in big V star. So we already showed that the kernel of f star is trivial. This shows that the only vector in kernel of f that's also in V star is the 0 vector. So we've proved the first thing. So now let's prove the second thing. Let V be any vector in the original domain, big V. Let W be the image under f of that vector V. Now, since f star is onto, its domain V star contains some vector V star such that f of V star equals W. So we have two vectors, V and V star. F of V equals f of V star. So f of V minus f of V star is the 0 vector. And then, using linearity, f of V minus V star is the 0 vector. So that shows that V minus V star, which we'll name U, is in the kernel of f. Changing this around a little bit, we can write V as the sum of U plus V star. That is, we've written V, the arbitrarily chosen vector in big V, as the sum of a vector U, which is in the kernel of f, and a vector V star, which is in big V star, the new domain. So we've proved the second thing as well. So this is what we've proved for any linear function. Here's an example. Let A be this matrix, and we define the function f from R3 to R3 by multiplication by this matrix. V1 and V2 are shown, and V star is the span of those two. The kernel of f is the span of this singleton set. It follows, therefore, that the original domain, big V, is the direct sum of the kernel, the span of this singleton set, with the span of V1 and V2. By the direct sum dimension corollary, the dimension of the original domain equals the dimension of the kernel of f plus the dimension of the new domain big V star. Now, since V1 through VR form a basis for V star, we know that the dimension of big V star equals R, which is also the dimension of the image of f. So what we've shown is, for any linear function, the dimension of the kernel plus the dimension of the image equals the dimension of the domain. We call this the kernel image theorem, and it's a very significant result in linear algebra and very useful.